Hello. So this is intended to be a substitute for the class session that I'll be missing on October 18th, which is a Friday. And yeah, I've already put out a video for the October 16th date that I missed or I will be missing. So this is sort of the second of two linear algebra videos. Today I want to talk about some new concepts and maybe this will feel a little bit more grounded in things that you're already familiar with because we're going to be talking about particular subspaces of Rn, the familiar Euclidean spaces that you are probably familiar with, maybe more so than your typical abstract vector space, by associating by defining certain subspaces that we associate to a matrix. The matrices, of course, being those are rectangular arrays of numbers, and so feel fairly, I hope anyway, familiar and not too alienating. And we want to prove a remarkable fact, which is that dimensions of two spaces, which at first glance might not look like they should have the same dimension, really do end up being equal to one another. Yeah, so let's dive in. It's going to be a lot of definitions and a lot of sort of technical work, I believe, having to do with matrix multiplication and all of that. So it's fiddly. But if you enjoy this, please scrutinize because hopefully I get all the details right. So the first thing that I should do is define for you what is meant by a few words. So definition. Suppose that A is a matrix. And let's go ahead and say that the shape of this matrix is going to be M by N. Okay, so it's got M rows and N columns. Okay, M and N don't necessarily have to be different, they could be the same. So keep that in mind, I suppose. Then we can talk about, now that we have the terminology, we can talk about the vectors that comprise the rows and the columns as representing spanning sets for certain subspaces of Rm and Rn. Now, this gets a little bit technical. So recall that when we defined Rn, or maybe I'll write Rk. So Rk, remember, we defined to be k tall column vectors. K tall columns. This is how we defined it to start with, right? But I want to also be able to talk about the rows, row vectors in A, things that are not tall but rather wide, if you like. And so there's a little bit of like an issue with like the like category errors. If I talk about elements of the rows of A as living in this space, there would be something wrong with that, right? Because rows of A, which by the way have what are, I guess, n wide. Yeah, there's n entries in each row, right? Because there's n columns. So there's n entries in each row of A. Those, strictly speaking, don't live in this space. So you, I guess, would like to distinguish the rows here with that. And if I want to be very careful about that, we would need a different notation for not the k tall columns. We need a notation for the rows, row vectors. And maybe one common way of doing that is to define what's called a dual space. Now, I'm not going to explain what this is from an abstract sort of linear algebra point of view. I mean, I can say the words. It's the collection of all linear functionals from Rk to the real numbers. But not so worried about that right now. Rather, we're just going to take this as the definition or as the collection of all k wide row vectors. and declare this is a vector space in kind of the obvious way. If you have two row vectors, you can add them entry by entry, and of course you can scalar multiply a row vector by a non-zero, or by any scalar, excuse me, and of course you'll get another row vector. So this is equally well a vector space, and we call it the dual of this one. That's how many mathematicians will think of it. But I'm going to be honest, it would be easier for me and maybe for you in thinking about it to just sort of conflate these two spaces, at least temporarily. Maybe we'll see. I can't quite anticipate what the where the issue is going to arise, where it'll feel like I'm talking about one space and then conflating that with the other. We'll see where exactly that crops up, but maybe I just want to address that issue so I don't, so I'm not telling you lies. These really are different spaces. They really are inhabit different species of animal, let's say. And so it's, I guess, important to distinguish. In any case, suppose A is an m by n matrix, okay? Then its columns live in, so where do its columns live? They're m tall column vectors, right? So they live in Rm, where K here is m. And the rows live in, yes, this kind of space here, Rk dual, K is in this case n. Okay, but we want to define what we mean by the row space and the column space. So definition, the row space of A is the span of the rows of A. That's it. And remember what we mean by the span of any collection of vectors in any vector space. That means the set of all linear combinations of those vectors. And then, of course, we can define the corresponding column space. And that's the span of the columns of A. Now, the feeling that you should feel is that these are very different kinds of beasts. First of all, we can say the row space of A is a subspace of a certain Euclidean space, or a certain dual of a Euclidean space. Okay, there's that issue, right? It lives in Rn. So you might visualize it being like an n-dimensional kind of subspace. Sorry, excuse me. No. I said that wrong. You might visualize it as a subspace of n-dimensional space. Okay. It isn't necessarily itself n-dimensional. Okay. Even though we might have m of these rows, and it could be that m is way bigger than n. It could still be the case that there's a huge amount of, like, let's say, redundancy in the list of those m rows, so that there's all sorts of like linear relationships among those vectors that would cut down the dimension of the space to some much smaller number. Do you see what I'm saying? Like, imagine that you had a matrix where every row, even though there might have been a lot of rows in the matrix, was a multiple of just one of the vectors. So, for example, let me just write things down. So, for example, suppose A was something like, I don't know, 3, 1, 6, 2, 9, 3. Okay, so there's 3 rows here. So this the row space of A would be the span of these 3 rows. So it would be the span of, let me be clear, the vectors 3, 1, the row vector 3, 1, the row vector 6, 2, and the row vector 9, 3. But probably you're noticing the thing I did to construct this matrix to make the pedagogical point. These vectors are all multiples of just the first one. So in other words, these 2 vectors here are in some sense redundant, right? They don't need to be included in the span. This spanning set it is a spanning set, but it could be shrunk. It can be shrunk down because there's something redundant about these, given that they are already multiples of this one here. So we could equally well express this span as the span of just one vector all by itself. 3, 1. Okay? In other words, in this case, the row space of A is one-dimensional. And where does it live? It lives in R2 dual. Okay? R2 dual. So like 2 wide vectors. And that's a 2-dimensional space. This is a 1-dimensional subspace. Okay. Now where does the column space, what does that look like? This is the span of 2 vectors now that are 3 tall column vectors. 3, 6, 9, and 1, 2, 3. Oh, shoot, whole point. My bad. Like that. Okay. But notice that this vector is a scalar multiple of that one. Just multiply this vector by 1/3 and you'll get that one. So there's something, again, redundant about this list. And we could rewrite this span not as the span of these 2 vectors, but just the span of one vector. The span of just 3, 6, 9. I hope that makes sense. Alrighty? So where does this column space live? It lives in R3. And the thing that we've been just vanilla calling R3 without this star indicating a dual space, whatever the hell that means. Okay, so whatever. Yes? Now, notice the row space of A is one-dimensional. Why? Well, this is in fact a linearly independent set, so in fact it's a basis for the row space. Notice also that the column space is one-dimensional. Why? Because this is a basis, again. And we know the theorem that every basis has the same number, every basis for a vector space has the same number of elements. We call that number the dimension. So evidently the row space is one-dimensional and the column space is one-dimensional. Huh. They're both one-dimensional. Even though, by the way, they live in kind of very different spaces and they look quite different from one another. This is like a line, okay, of vectors in R2 passing through the point 3, 1, if you like. I don't know if you want to visualize it like that. It's the collection of all vectors like that. That's fine. And then this is the set of all vectors in 3-dimensional space, which are scalar multiples of 3, 6, 9. But one thing that these 2 spaces have in common, it turns out, is that they have the same number of dimensions. That's not a coincidence. And that's one of that's the theorem that I want to try to prove for you today. And there's going to be a lot of work in order to get up to that point. Okay, but let's keep establishing terminology to make sure that we understand what's happening. Okay, we're going to call further definitions. We're going to call the dimension of the row space the row rank. Is the dimension of the row space of A. So hopefully, I guess I didn't establish this notation, but this is probably descriptive enough on its own. Row space of A is a vector space. It's spanned by the rows of A. And then I'm asking about the dimension of that. Okay, so this is a vector space. I'm then asking about the dimension. This number, this positive or rather non-negative integer, is what we call the row rank. Okay, and similarly, the column rank of A is the dimension of what I'm going to write down as the call space of A. And I hope that that's descriptive enough. Oh, I don't know. I guess I like being. Oh my God, I'm really gonna do it. I've got mental issues. The row space of A here is the denoted row space. Oh, row space of A. And the column space of A is denoted col space of A. Okay. So these are vector subspaces of a familiar space associated to a matrix. Okay, great. The theorem that we want to prove, and I'll announce it, is that the row rank of A is always equal to the column rank of A. That the fact that this was one-dimensional and this was one-dimensional and that 1 is equal to 1 is not a coincidence. That is what happens all the time, always, for any matrix A. So for any matrix A, row rank of A is equal to the column rank of A, which is crazy, okay? And actually, it makes me happy in trying to highlight the craziness of this result. It makes me happy that I went through this little discussion up here. Because please understand, the row rank being the dimension of the row space, well, the row space lives in this vector space of row vectors. Whereas the column space lives in the vector space of column vectors. These are two separate universes from one another. And yet, it somehow happens, and these two spaces can look radically different from one another. I mean, they're both one-dimensional. That is what they have in common. But they're like, it's hard to see how this is related to that. You know what I'm saying? There's something difficult about seeing what their relationship is. They live in different universes, so it's hard for them to have a good relationship, and yet it will always be the case that the dimension of the row space will be equal to the dimension of the column space. That's the theorem that we want to work hard to try to prove today. Okay? Now we have to develop some machines in order to get here. One thing that is probably obvious, okay, is that you can always think of the column space of, or the row space, let's say. Here's how I want to say it. Definition. I'm going to define something, and then we're going to see a fact. Actually, I'm sorry. Let me say it differently. Suppose we look at this example again, and I'm going to define another matrix, and here's how I'm going to define it. Define a matrix, which will be A, and I'm going to denote it like this, A, and I'm going to put that T in the superscript, okay? I'll just say it's A transpose. T stands for transpose because T is the first letter of the word transpose. And I'm going to define this more formally. But for this matrix A, I want to define A transpose to be this matrix. 3, 1, 6, 2, and 9, 3. Oh, okay. See, now this is a moment where... Okay. Then notice that, well... if I take the column space of A transpose, okay, that's the span of these three vectors here, by definition. Nine, 3. But exactly the same considerations that we talked about up here apply to this space. That is to say, notice how up here, remember, we said, oh, these two vectors are simply scalar multiples of this one. This one is twice that vector, and this one is 3 times that first vector. And so we may as well just express the span of 3 vectors as the span of 1, namely the first one, 3, 1. We can give the exact same argument here. This is the span of 3, 1. Now, you might be saying to yourself, whoa, well, doesn't that mean these are the same? But this is where that issue is coming up. I sure would like to say that they're the same. But the problem is that this is a column vector here, and that's a row vector there. So it feels like they live in different universes, but they're really kind of the same universe. Is that a fair thing to say? That there is a really easy way of going from this space, which lives in, by the way, R2 dual. So this one is in R2 dual, the two wide row vectors, whereas this one lives inside of just vanilla R2. But it sure feels like these really are the same. That you can somehow get at the column space of A transpose, okay? Or sorry, the row space of A by looking at the column space of A transpose. And I want to take advantage of that. I definitely want that because that's going to, I think, enter into the proof that of this theorem here. This theorem, which I'm going to call theorem star. That's not dual. That's theorem star, which is going to be the main theorem for today. So what I'm trying to get at here is that if you take what's called the transpose of this matrix, and I'll define that formally in a moment. If you take the transpose of this matrix A, then the column space of the transpose is, in some sense, the row space of A. If you are willing to sort of ignore the category error of these two spaces being completely different universes, okay? There's something just that's hard to resist about equating these two things, okay? All right, great. I feel like I've done my due diligence in like saying all of those words out loud. And so maybe I'd never have to say them again. Is that possible? We'll see. And also notice that the row space of A transpose is the span of the two rows 3, 6, 9, and 1, 2, 3. And again, we don't need both of these. One will do. Okay. And I kind of want to say, look at that one with that finger, and look at that finger. Okay, look at those two subspaces. Those are like the same, kinda. Except that they live in radically different universes, but somehow those universes are the same universe in some sense. Okay, one's got rows in it, and one's got columns living in it. Yeah. Okay. So we can sort of get a feel for that, but in particular, maybe this is clear. So even though these things live in different universes, maybe this statement is clear. It's clear. It's always dangerous to write this in mathematics. It's clear that the row rank of A transpose. Okay, so what am I talking about here? I'm talking about the dimension of the row space of A transpose is exactly the same thing as the column rank of A. And the column rank of A transpose is equal to the row rank of A. That part probably is less controversial, right? It's not that, okay, yeah, maybe what I was saying was too strong. I'm just thinking out loud here because, you know, maybe it's too strong to say that in some sense these are equal. They do live in separate universes, but maybe it's not as controversial to say these two statements that the row rank of A transpose is equal to the column rank of A, and that the column rank of A transpose is equal to the row rank of A. Just by looking at the structure of these spaces here, you can see that they're the same. Yeah. Okay. Maybe I feel more comfortable about that. Now, let me define formally what I mean by A transpose. Definition. Oh, and just let's establish some notation for the entries of a matrix. So, given any matrix A, let's define, for convenience, if I write A with ij in the subscript like this is going to be the ij entry. That, in other words, is the entry in the ith row. Sorry, the glare from my light here is pretty intense, isn't it? Maybe I can make it more diffuse this way. This is the entry of A in the ith row and j's column. I might have defined this already. I don't remember. So it's fine if I just do it again. Yeah. Okay. Then we can give another definition now for the transpose. The transpose of A, the transpose of A denoted A transpose is a matrix whose ij entry is the I just established this notation, but I didn't use it. Whose ij entry is the ji entry of A. Yeah. So if I do use this notation, what I'm saying is that the ij entry of A transpose is equal to the ji entry of A. And that's a lot of letters to write down. But basically, the idea is that A transpose swaps the role of rows and columns. Oh God, we're doing it again. It makes the rows of A into the columns of A transpose, and the columns of A become the rows of A transpose. So just as a quick example, if A is the matrix 1, 2, 3, 4, 5, 6 with 2 rows and 3 columns, then A transpose swaps the rows and the columns so that the new first column of A transpose is the first row of A, but written vertically. And the new second column of A transpose is the second row of A. And notice that this also makes the rows of A transpose the columns of A in some sense. Yeah. Oh my goodness. What? I probably should have just not mentioned this thing at all. And probably everybody would have been content, except my brain would have been screaming because I've got mental issues. It's clear. And similarly, a B is, let's say, the row vector, or let's say it's the column vector 7, 8, 9. Then B transpose is the row vector 7, 8, 9. Like that. Okay. And you can see, check that in these examples here, this sort of condition here is satisfied. Okay. One basic fact. So some facts about transpose. If A is m by n, that is to say, if its shape is m by n, then obviously A transpose is n by m. got n rows and m columns. Okay. Another fact which is pretty easy to see is that if you take the transpose of the transpose, that's just the matrix itself, right? Another fact that's pretty easy to see is that if you take the sum of two matrices, okay, if both of these are n by m, or m by n, and you can take that so that you can take their sum, then the transpose of the sum is pretty easy to see that that's the sum of the transposes, A transpose plus B transpose. Okay, that's fine. But what's a little bit less fine is what happens or how transpose interacts with products. So if you take, and this is important, if you take the transpose of a product, A times B, it turns out that that's B transpose A transpose. Okay. Yeah, this is important. And probably we should prove that last one. Okay. Yeah, that's an easy proof. Okay. But first, let's just make sure we understand this statement here, and then I can prove it. So imagine A is m by n. Oh, and maybe I should say, okay. So if A is m by n, maybe if this is A here is m by n, then remember that B has to have the same number of rows as columns of A in order for this matrix multiplication to make sense. So this has to be n by something, and I could call this something P. It doesn't matter what it is, okay? But n by P, so that this matrix AB has dimensions m by P. Does that make sense? So that the transpose has dimensions P by M. Now, if you were naive and were to say that AB transpose was just A transpose B transpose, that is to say, not what's written here, but in the other order, I think you would get a dimension mismatch. I think that would be a problem because B transpose is supposed to be P by N, and A transpose is supposed to be N by M, so that this product makes sense. Whereas if we were to swap the order of A transpose and B transpose, well, then we wouldn't have the right sort of, there would be a dimension mismatch, which would cause this mapmul to go awry, right? Python would throw back an error at us. Okay. So there has to be some statement like this, and I guess it's the nicest possible one that you could possibly hope for, given this dimension condition here. But let's prove it. Let's prove it. To prove it, I want you to recall something about matrix multiplication. Right? Yes, I think so. So recall, if A is m by n, and let's say B is n by p, then we can say something about, oh, yes, nice. We can say something about the ij entry of the product of A and B, right? The ij entry is equal to the sum from k equals 1 up to n of, okay, we're going to take the ith row of A, the ith row of A, and sort of interleave it with the bth column, no, the jth column of B. So that's AIK, no, sorry, I don't know why I wrote it a lowercase, AIK times BKJ. This is correct, yeah. This is just the definition of matrix multiplication. But that's a useful thing to sort of have in our brain because I want to prove this statement, which is evidently going to use this matrix multiplication quite intimately, right? It's going to get all up in there. All right, so let's prove this. Proof that AB transpose is equal to B transpose A transpose. And this is really just working through this definition here. So uh, um, the let's look at what the IJ entry of AB transpose is. So AB transpose IJ. All right, so I'm sort of mixing up all sorts of notations here, okay? This means I'm taking the transpose of the product of A and B, and I'm looking at the ijth entry of that. Well, by definition, this is the ji entry of AB without the transpose. That's by definition of the transpose, right? The ij entry of A transpose is the ji entry of the non-transposed matrix. So that's where we got this from. But by this fact, okay, this fact, yeah, this is equal to the sum from k equals 1 up to n of the, so it's the jth row of A. So here's us, as k runs through from 1 to n, we're going through the jth row of A, and we're interleaving that with the ith column of B. Like this. So this is an application of this factoid right here. Cool. Now I'm going to write this in the other order, I think, because I guess I'm trying to get this to look like the ijth entry of this. So I'm going to use this is just me using the commutativity of multiplication of real numbers, and I get bki ajk. I just literally write these in the other order. See? But bki is the ikth entry of B transpose. And ajk is the kj entry of A transpose. But now we can use this again, okay? Where what's playing the role of big A, I'm looking at the right-hand side of this. What's playing the role of big A is B transpose, and what's playing the role of big B is A transpose. And that's evidently supposed to be the ijth entry of the product of B transpose with A transpose. So this is B transpose A transpose IJ. Okay? So what I've done is shown that the ijth entry of AB transpose is equal to the ijth entry of B transpose A transpose. That feels pretty good. That means that these matrices are entry for entry equal to one another. And so that proves it. Okay, great. All right. So let's see what comes next. All right. So don't forget what the prize is, what the big theorem that we're trying to prove is. We're trying to prove that for any matrix A, that the row rank of A is equal to the column rank of A. Let's just put this in a red box to emphasize that this is the main theorem. This is the thing that we're hunting for. We haven't proved it yet, right? We are just building up machines right now to maybe prove it. And this is sort of how you sniff about trying to prove things, is that you notice certain patterns. Like we notice this sort of relationship between the column space of A transpose and the row space of A. And yeah, you just sort of start building up machinery in order to get things done. Okay, what I want to do right now, I noticed that we're at the 40-minute mark, so I've got about 30 minutes or maybe a little bit less than that to prove that theorem in red. Is just take a little bit of a breather, take a 5-minute break. I'm going to collect my thoughts because I think this gets a little bit technical. If it hasn't already been a technical discussion, it's going to get, I think, a little bit worse. So I should organize my thoughts clearly about what it is I want to say. So I just want to be honest with you. That's what I'm going to be doing now. You might take this opportunity to go get a drink of water or whatever, and let's sort of persevere and get through the final part of the proof of this red theorem here. Okay? So take a break. Bye. Okay, so hopefully my thoughts are sufficiently collected on this. I think that we're going to need to recall one important fact that has to do with the mechanics of matrix multiplication. So let me, and we've mentioned this many times, but it's worthwhile to say it again and again because I remember when I first learned this topic, this was not made clear to me at all, or I didn't feel that way anyway. So here's what I want to say. And I'm trying to be mindful in anticipation of like future notational constraints that I want to make sure that we don't run afoul of. So this might look a little different than previous explications of this same fact that we might have had previously, but that's okay. So let's say that we have a matrix A for a moment, okay, and let's say this is m by n. And we know that we can multiply this matrix by vectors, by n tall column vectors. So let's say that we have an n tall column vector, call it x. So x is going to be an element of R n. Then we can form the matrix A times x. And A times x is an element of Rm, right? And in particular, A times x is a linear combination of the columns of A. It's not just anything, it's a linear combination. In other words, now that we have the terminology, A times x is an element of the column space of A. Okay? And what linear combination is it? Well, it's the one that we get by looking at so sorry. Let's be very clear. So if A is divvied up into columns like this, if this is A1 and then going all the way out to how many columns are there's n of them, okay? So if A has n columns, A1 through AN, each of these are elements of Rm. And X is the column vector whose entries are x1 through xn. Then AX is equal to x1 times A1 plus x2 times A2. I don't know why I did that. All the way up to xn times an. And this is just knowing or understanding this just is a matter of just tracing through the calculations, okay? I expect you know how to do A times X, but maybe the realization that it ends up being this particular linear combination of the columns of A is a little bit less obvious, okay? Well, it turns out, okay, that we can sort of extend this this kind of calculation by stacking these sorts of calculations kind of horizontally expanding it out. So what do I mean? So right now A is m by n, and x here is n by 1. But what if we took the 1 in n by 1 and made it bigger? Okay, so in other words, that would make this x here expand kind of out horizontally, right? It would expand out like this way with more entries into a matrix with n rows and, I don't know, p columns. Can we imagine? And then we can ask about A times that new matrix. So imagine, and I'm going to call it big X now. Big X is an n by p matrix whose let's say xij, let's say x is given by a column wise x1, x2, all the way out, etc. to xp. Okay. Then we can form the product ax, a big X. Now let's do a shape check here. A is m by n, x is n by p, so the product is m by p. Okay. And so the columns of ax are elements of Rm. And we know that if we take A and hit it with one of these xi's, we get an element of Rm. In fact, this is equal to a matrix whose first column is A times x1, whose second column is A times x2, etc. And I think there are p columns total. Lovely. I don't want to prove this, okay? I don't think it's hard. I think you can do it. But I do want to assert it as a fact for us to use. In other words, the columns of A times X are really these linear combinations where, again, so A times X1, okay, for example, is a linear combination of the columns of A, okay, where the coefficients of that column, the x's here, are the entries of the x of this vector x1. Similarly for all the other columns of A times big X. All right? Okay, all of that's going to be, I think, useful for us. All right. Okay, so now proof of theorem star. What was it again? What was theorem star again? For any matrix A, the row rank of A is equal to the column rank of A. That's what we want to prove. All right. I'm a little scared. We're going to get through this. We're going to persevere, okay? Got like 20 minutes, okay? That's fine. We're going to do our best. So, yeah, let's say we have A, an m by n matrix. And we are going to let the column rank of A be R. Okay? So small r is going to denote the column rank of A. Now, let's define a basis for the column space of A. I haven't talked about how to compute the column space or how to compute even a basis for the column space, let alone a column basis for the column space. But the column space exists, as you can imagine. It's just the span of the columns. And maybe I didn't say out loud, but every vector space has a basis, okay? And we're just going to take that as a fact. I don't want to prove it. It turns out that the proof is a little bit controversial in and of itself, particularly if you want to have that discussion include in its scope infinite dimensional vector spaces. But I don't want to get distracted. let's just assume that a basis for the column space exists. And let's let, we're going to say C1, C2, all the way up to CR be a basis for the column space. So sanity check. These are R vectors. Why? Because the dimension of the column space, which is aka the column rank of A, we define to be R. Remember, R doesn't have to be the number of columns. The dimension of the column space is not necessarily equal to the number of... What did I just say? Let me rewind and say what I want to say again. Remember that the dimension of the column space, aka the column rank of A, is not necessarily equal to the number of columns of A. And that's because the columns of A can have redundancies in them, which shrink the dimension down from n down to some possibly smaller number R. Does it have to be smaller? No. Can it be smaller? Yes. So we're going to declare R to be the rank, and therefore this basis must have R elements in it, because every basis has R elements. Every basis of the column space of A has R elements. So we declare this is 1. Okay, then we are going to form a matrix out of these columns. Let big C, okay, be the matrix whose columns are exactly this. CR. And this has shape, and I'll just sort of note this in green. This has, maybe I'll write it out. Then C has shape. So the number of columns is easy. We wrote that out. It's R columns. How many rows does it have? I believe it has M rows. This is an M by R matrix. Okay. All right. Now, this is a basis for the column space, okay? So what we can do is we can express every column of A. We can express every column of A, like up here. Every column of A can be expressed uniquely as a linear combination of this basis. The linear combination of these basis vectors. Okay? If AJ is the jth column of A, jth column of A, then because C is a basis, we can uniquely express AJ as a linear combination of elements of C. Okay, so yeah. So AJ, in other words, the jth column of A is equal to, let's call it X X1J times C1 plus X2J of C2 going all the way up to x. X R XRJ. Sorry, I got lost in the sauce there. XRJCR. Phew. Okay, there we go. So this is the jth column of A expressed as a linear combination of the basis vectors C. But then what we can do is take these coefficients and form those into a column vector. So let xj, okay, xj, same index as this one, be equal to the column vector x1j all the way down to xrj. And form the matrix X, whose jth column is x sub j. So this is the first column is x1, second column is x2, and this goes all the way up to what? Yeah, this is the number of columns. So this is xn. There are n of these, right? Because, okay, so yn, not r, yn, n. Because there are n columns of A. So I can write sort of n equations of this form. I can take all those coefficients, organize them into a column vector like this, and stack all those horizontally into a big matrix X. And to be clear about this matrix, this is, how many rows is it? And how many columns is it? It's got R rows and N columns. Yes. Yes. Okay. Okay. Good. Here's the claim. A is equal to C times X. A is equal to C times X. Now, first, dimension check real quick. C, we said, was M by R. X is R by N. So C times X is the correct dimensions. It's M by N, for A, which agrees with the shape of A. Okay, that's cool. But, so can I just write this? So, so A is equal to C times X. Now I want to, so yeah, this dimensionally makes sense because that's, sorry, this is M by R and that's R by N. Therefore its product is M by N, which is nice because that's exactly the shape of A. Okay. But we just got done talking about how when you take a product of matrices, okay, each column of the product is a linear combination of the columns of A. So each column of CX is a linear combination of the columns of C, but the columns of C are the basis elements. And what linear combination do we get for each of the columns here? Well, that's exactly the construction of the jth column of A. Like that's exactly this linear combination. Does that make sense? Which is why we can say the jth column of C times X is precisely the jth column of A. Does that make sense? I hope I said those words in the right order. Yeah. This is because the jth column of Cx, okay, is, well, it's C times the jth column of X, but the jth column of X is precisely those entries in this vector X sub j, which are used in the construction of A sub j as a linear combination of the C's. Is C times X sub j, okay. This fact that the jth column of Cx is just came from this discussion up here. But this is exactly, and then I'll say by construction, the jth column of A. So what I'm saying is that this is true because these matrices are column by column equal to one another. Okay, great. All right. Okay. Now, and this is a key moment with this factorization, now we're going to use the transpose. All right, so let's just take a moment. Okay, so the column rank of A is R. Now we're going to take the transpose of this product here. All right. This is equal to X transpose C transpose, right? Oh, why did it, because that's the theorem that we proved about the transpose of a product, right? It reverses the order of the factors. So what this is saying, now we can think about the columns not of A anymore, but of A transpose. And what this is saying is that every column of A transpose, okay, well, again, by the exact same sort of consideration that we made up here, where, okay, so we have a product, X transpose C transpose, right? The columns of X transpose C transpose, okay, are things of the form X transpose times some column vector. In fact, which column vector? A column vector in C transpose. Yes, all of those words are true. And when we form, yeah, so let me write this down. Then we can conclude the columns of A transpose, okay, are themselves linear combinations of the columns of X transpose. Which linear combination of columns of X transpose? Well, take the like if you were to think about the jth column of A transpose, then you would take the maybe I don't want to say jth, maybe I want to say ith column of A transpose. That would be taking the ith column of C transpose, okay, using those coefficients in a linear combination of the columns of X transpose. Yeah. Now, the point is that this implies that the column space of A transpose sits inside the column space of X transpose. I'll say is a subspace. Ooh, maybe I didn't. Okay. Is a subspace of the column space of X transpose. Right? Because every column of A transpose is already itself a linear combination of columns of X transpose. So the column space of A transpose sort of sits inside, naturally, the column space of X transpose. But what is the dimension of the column space of X transpose? I don't know exactly, okay? Notice, though, that the dimension of the column space of X transpose so the column space of X transpose, remember that's the span. So this column space is the span of the columns of X transpose. So this dimension can't be bigger than the number of columns of X transpose. Sorry. This is less than or equal to the number of columns of X transpose. But what is the number of columns of X transpose? Remember, X was R by N. So X transpose is N by R. So this is equal to R. The dimension of the column space of X transpose is less than or equal to R. Okay. But remember what R was? R was, what is R? R was the dimension of the column space of A. But now we're saying that because sorry, I should make one more conclusion. Because A transpose is a subspace of the column space of X transpose, we know that the dimension of the column space of A transpose is less than or equal to the dimension of the column space of X transpose, which is less than or equal to R. Now, so we've got what's called an upper bound on the dimension of the column space of A transpose. It's less than or equal to R. And by the way, remember from the observation, the it's clear observation, the column space of A transpose, its dimension, which we call the column rank of A transpose, is equal to the row rank of A. So this is also equal to the dimension of the row space of plane A. Okay. Now, so this is good and true, but we could do all of this, okay? Okay, okay, right. Better to write this. I'm sorry. Better to write this. Dimension of row space of A, okay? This is the dimension on the nose of the column space of A. Okay, so now I just want you to look at what we've got. We've got that the dimension of the row space of A is less than or equal to the dimension of the column space of A, where the dimension of the column space of A is R, okay? But we can now give the exact, because this is true for all matrices, okay, we could give the exact same argument, not about A, but about A transpose. Apply this to A transpose. And what you learn is that the dimension of the row space of A transpose, okay, so all I'm doing is replacing the A here by A transpose there, is less than or equal to the dimension of the column space of A transpose. Okay, so all I've done is replace the A here by A transpose. So we get this. But this one we can refer back to. This is just the dimension of the column space of A. Why? Because of the it's clear statement. Okay, the row rank of A transpose, which is this, is equal to the column rank of A. Neat. And so this is evidently less than or equal to the dimension of the row space, the row rank of A. Okay, so now I want you to take account of these two inequalities. Here's one in green, and here's the other one that I want you to pay attention to. How could it be that the dimension of the row space of A is simultaneously less than or equal to the dimension of the column space of A, but also greater than or equal to the dimension of the column space of A? There is only one way, which is if these two numbers are equal to one another. Oh, I don't know why I did that. Equals the dimension of the row space of A. And that's it. Wow. If you understood all of that, congratulations. I think that was quite a journey. But I think it's all there. None of the details were sort of left out or obscured. It's all there. It really relied, of course, on this fact that this it's clear statement, which hopefully is clear, and which sort of gets at trying to. Well, I think it's pretty clear, right? I think it's pretty clear. So I'm pretty satisfied with this proof here. I'm noticing that I'm just 50 seconds below time on this video. That's good. Yeah. Now, what's going to happen is we're going to start talking about just the rank of a matrix A. So that rather than having to fiddle about with row rank and column rank, we no longer have to do that. Now that we have this theorem, we can just talk about the rank, okay? The rank of a matrix is a very, very important quantity. We're going to use it a lot. We're going to think about it a lot. And it has some important, well, it's just important, okay? It's important to know about. But now we know this miraculous theorem that even though these spaces, the row space and the column space, feel like they live in different universes, one thing that we know, no matter what the matrix is that they always have the same dimension. Okay, cool. That's enough for today. Hopefully, I'm not, as you're watching this, I'm not currently dead in LA, and I will see you October something. Someday. I'll see you soon. Okay. Bye. Love you. See you. Bye.